Hello everyone. In this lecture, we will discuss about the oxidative and non-oxidative part of aging of bituminous materials and how nitrogen conditioning can be used to separate these two. So this is the outline of the presentation. We will see what is the effect of experimental conditions on the aging and how to separate the non-oxidative from the oxidative aging, and also discuss about the aging during production of polymer modified bitumen. I've taken some photographs and pictures from Google sources, and my sincere acknowledgement to all these sources. So in this course, we have already discussed about what is short-term aging and what is long-term aging. So short-term aging is the aging that happens to the bitumen during the production process of HMA and the compaction process within a few hours of its production. And long-term aging is the aging that happens over a period of time during the service life of the payment. And these processes happen, or the aging happens due to various processes such as oxidation, volatilization, steric hardening, polymerization, etc. Now, of these, during short-term aging, there are essentially two things that happens. One is the fast oxidation of the material, and second one is a non-oxidative or a thermal effect. This oxidation happens because of the high temperature and also the large specific surface of the bitumen, which is available during this high temperatures. And the physical effect is that there will be evaporation of the removal of the volatile compounds from the material. Whereas in the long-term aging, it is essentially an oxidative process, which is slow in nature because of the presence of this oxidant gases that are available in the atmosphere, like ozone, nitric oxide, etc. And this aging happens for the material at the top layers of the pavement. Now, how do we simulate this aging in the laboratory? Is again, we have discussed this. You use a rolling thin film oven and test to simulate the short-term aging of the binder, and a pressure aging test on the RTFO age specimen to simulate the long-term aging. Whereas the hot mix asphalt is concerned, there are many laboratory aging procedures where the mixture or the compacted asphalt mix is subjected to higher temperatures in the laboratory. Now, all these processes depends on increasing the temperature or pressure of the sample, so that this aging that happens in the field over a period of time can be conducted, or can be simulated within an efficient amount of time. Now, when you look at the long-term aging temperature or conditioning temperature, the temperature is of the order of 90 to 110 degrees Celsius, which is higher than the usual surface temperatures that happens in the field. Now, there is a possibility that non-oxidative effects also happen at this high temperatures, which causes a further vaporization of the volatile binder components, which does not happen in the field usually. Now, what should be the right choice of temperature and pressure, or why is it important? Now, as per the collision theory by Tross, the speed of the chemical reactions or the successful collisions depends on various factors. One is the particle concentration. So if you have higher particle concentration, higher will be the chances of successful chemical reactions. And if you increase the temperature, that accelerates the particle speeds, which again increases the reactions. And also increasing the pressure will in a way lead to the higher particle concentration, which in turn can lead to a higher reaction speed. So what will be the rate of reaction can be explained using the reaction rate temperature rule, or it's called the RGT rule, or the 10-degree rule, that the thermal aging is usually doubled for every temperature rise of 10 degrees Celsius. This is further explained using the Arrhenius relation, wherein the frequency of collisions in a reaction K is given by the Arrhenius equation A raised to minus EA by RT, where EA is the activation energy, T is the absolute temperature, and R is the universal gas constant. So from which we can see that the aging temperature will have an exponential effect on the laboratory aging of the bituminous materials. Now, if you look at the relation between the temperature and viscosity, at higher temperatures, the binders will have a lower viscosity, and at this viscosity, it will be able to form a thin film, So we know that it will having a thin film around the aggregates, so it flows more easily, and surface of these thin films will be easily attacked by the reactive oxygen species which are available in the atmosphere, and the aging process will get increased. Okay, so there are two effects here. One is the increased velocity of the chemical reactions that happen because of the high temperature, and the second is the decreased viscosity, which will lead to a higher surface area and hence an increased aging of the binder. So there is a enormous aging or a duplicate effect of aging that happens when you actually increase the temperature drastically. Also, there are studies which have tried to understand what is the relation of this uh, temperature or the effect of the temperature on the aging conditions. It is shown that no chemical changes are observed at 60 to 130 degrees Celsius in the absence of oxygen, whereas some small amounts of volatiles may be lost at elevated temperatures. And also temperatures above 150 degrees Celsius, there could be non-oxidative reactions may begin to cause chemical changes in the material even without the presence of oxygen. And Reed et al. Has shown that the loss of volatile starts at 150 degrees Celsius and it gets doubled with every 10 to 12 degrees Celsius rise in temperature as per the RGT rule. And sulfoxide decomposition and the disruption of polar molecular association starts at temperatures even at 100 degrees Celsius. So there are other approaches which are tried so as to simulate it more effectively. One such approach is to keep the temperature in a realistic range, say 60 degrees Celsius, then maximize the presence of the oxidant gases in the atmosphere so that the aging will be affected by the gases which are available, whereas the rise in temperature will not cause much of an effect. So, or the temperature will not cause much of an effect. So, this is one way of achieving an acceleration of the chemical reaction instead of increasing the temperature than the realistic values. Now, Steiner et al. In 2018 has conducted a study to separate this oxidative part of aging from the non-oxidative aging. So in this method, several HMA samples were tested or aged under the atmospheric age condition, and in order to cause a non-oxidative atmosphere, nitrogen is used as a conditioning agent. So this the specimens are subjected to a nitrogen atmosphere so that whatever aging that happens at an elevated temperature of conditioning will be due to non-oxidative effects, and no oxidative effects will happen at that condition. So this is the setup that was used. You can see the specimens which are placed here with filter stones in between, and it is placed inside a clamp, in a tube clamp, and a continuous supply of nitrogen is given to the specimen, and the conditioning is done at different temperatures of 60 degree, 85 degree, 100 degrees, and so on. And here in this condition, the nitrogen atmosphere will prevent any oxidative aging and will trigger only non-oxidative aging. Now, similar specimens were again tested in a air conditioned condition also. Now, after conditioning the specimen for 3 to 4 days, they are then tested for the dynamic modulus. So this figure shows the relative change in dynamic modulus, or it's a ratio of the dynamic modulus of the aged specimen to the unaged specimen. And here, the test conducted at 5 Hertz frequency is presented. You can see that this diamond-shaped bullets show the specimens, results of the specimens which are conditioned under nitrogen, and the circle bullet points indicates the test results for the specimens which were stored under air atmosphere. So we can see here with the nitrogen aging aged specimens, any significant changes happened only after 85 degrees Celsius, and there was no changes when the test was or when the conditioning was done at 60 degrees Celsius. When I say the significant changes, any changes more than 5% is considered to be significant, and less than that is, or 5% is taken as a reliability range for the repeated indirect tensile test that was conducted for this study. Now, as we can see here, for the atmospheric air-aged specimens, significant changes has been seen in all temperatures of aging, such as 60 to 135 degrees Celsius, and always it is seen that the air aged specimens were stiffer than the nitrogen aged specimens. And next shows the change in the phase angle of the aged versus unaged sample. And here, any change which is more than or decrease in phase angle more than 2.2 degree is found to be significant or is shown to be significant. And it can be seen that the significant changes occurred at 85 degrees Celsius for the atmospheric aged specimens, whereas any such significant changes could be seen only after 110 degrees Celsius for the nitrogen aged specimens. So, as we can see here, this nitrogen aging could successfully cut off the oxygen aging and show only the non-oxidative aging part. So this changes or the separation of oxidative and non-oxidative aging is presented in this plot here. We can see that at 85 degrees, so this is the white colored box shows the non-oxidative aging, which was captured from the aging done at nitrogen conditioning, and the black box indicates the oxidative aging. So we can see here the non-oxidative aging happens only after 85 degrees Celsius, whereas the effect of oxidative aging is very substantially higher as compared to the non-oxidative aging part, especially at higher temperatures of 135 degrees Celsius. Now, in order to understand what is the behavior of the binder in these mixtures, the binder from the mixtures after aging were later extracted using tetrachloroethylene solvent, and a temperature sweep test was conducted from 46 to 82 degrees Celsius at a frequency of 1.59 Hertz, and the results are shown here. We can see this is the shear modulus of the aged sample to the shear modulus of the virgin sample. As you can see here, again, this is any change which is or the RTFO as well as the PAV aging is also from the literature is also shown in the picture. So we can see here the diamond-shaped ones are the aged specimens from the nitrogen-conditioned specimens. So we can see here the changes is very less, or the changes between the temperatures is very less, and significant changes happened only after 135 degrees Celsius, whereas in the air-conditioned specimen, you can see that the mod G star has significantly increased after 110 degrees Celsius. So one thing to be noted here is that the binder, when you say the unaged binder or the virgin binder, it is a very base, the binder before being used for the casting. So when this hot mix asphalt is being prepared, there is a short-term aging that happens to the material. So that part is included in this the short-term aging or the non-oxidative aging in the case of the binder, because during the preparation of the mixture, that aging also is there. Now, what we have discussed so far is the oxidative and the non-oxidative aging in the unmodified binders. Now we know that we normally do a modification of binders. There are different types of modifications, polymers, scrum rubber, natural rubber, etc., of which polymer modification is a very commonly adopted one. The compatibility of a modifier bitumen depends upon various factors such as the molecular weight of the polymer and the bitumen, the polarity of the polymer, the nature of the base bitumen and the polymer. So when I say the nature of the base bitumen, your base bitumen also could be from different sources, from the different manufacturing process, such as there could be an air rectified base bitumen, or it could be a component blended one. So based on the type of the base binder as well as the polymer that is used, this the compatibility varies. And also another important aspect is the mixing conditions of the polymer with the base bitumen. So when you add a polymer to a base bitumen, there could be different types of interactions. One is a physical interaction, then chemical interaction, or an inert interaction. So in the physical interaction, essentially the swelling of the polymer happens because the polymer will absorb absorb the lighter fractions that are available in the bitumen and then swells. And this will add to the formation, or this will lead to the formation of a network of polymer, which adds to the stiffness of the modified binder. There could be other reactions. One is a chemical, which is a chemical reaction, wherein the polymer chemically reacts with the bitumen and forms new compounds. Whereas in the inert reaction, the polymer will act as a filler. Now, if you look at the modification of bitumen with elastomeric polymer like styrene butadiene styrene or SBS, it is essentially a physical interaction, okay, wherein the swelling of the SBS happens between cross links. The polymer volume normally increases to a rate of 9 to 10 times its original volume, and it will swells all the lighter fractions that are available, which is the saturates and the naphthene aromatics present in the bitumen. Okay, so we can see from this figure, you have the bitumen matrix, which has the asphaltene particles, and the maltene matrix, so that are the lighter fractions. Now, when the polymer is being added, the polymer absorbs these lighter fractions and it swells. So there are two ways in which the enhanced behavior of the modified binder happens. So one is that from the binder, all the lighter particles are absorbed, and there will be a agglomeration of the asphaltenes that happens, which adds to the viscosity of the material. And the second is the swelling of the polymers that happens, and causing this 3D network with an increased viscosity. So both these happens, and due to this combined effect is what the polymer modified binder gets its performance. Now, what is very essential here is that there should be the availability of these lighter fractions for this polymer to absorb and behave, okay, and respond in that manner, in a better way. So when you do the production of a polymer modified binder, normally this modifier is added to the bitumen, and it under very high temperatures and shear rates. So there is a possibility of aging that happens during this production of the PMB itself, which will again depend upon the type of the base bitumen, the type of the modifier and the dosage that is used, and of course the condition of the production process. That is, what is the duration for which these are mixed together, and what is the temperature at which it is being mixed, and the atmosphere that is available. So essentially, when you consider a polymer modified binder, there is 3 stages of aging that can happen. One is the aging that is happening during the production of the polymer modified binder. Second is the short-term aging, and the third, of course, is the long-term aging, when it is being mixed with and compacted with and used in the so the short-term and the long-term aging happens with the mixture, whereas the initial aging happens with the production of the modified binder itself. So in order to understand this aging of polymer modified binder during the production process, we've conducted a study at IIT Madras, which is sponsored by the SERB DST, wherein an elastomer SBS is used as a modifier, and the production involved a small scale as well as a high shear blending process at 135 degrees Celsius. So in order to separate out the effect of this aging due to the presence of air, and also the absence of oxygen, conditioning with and without nitrogen was used during this production process. And in order to the performance of the modified binders when they were produced at in the nitrogen conditioned atmosphere as well as the air atmosphere were tested using various experiments. So what is presented here is the rut resistant behavior, which is determined using the multiple stress creep and recovery test at a 1 second loading and a 600-second recovery at 2 temperatures of 50 and 60 degrees Celsius. As you can see here, the red line indicates the specimens which were conditioned where the binder, which was the polymer modified binder, which was prepared under the air atmosphere, whereas the blue line indicates the preparation that was done under nitrogen conditions. So what you can see here is that the creep response of the material, or the creeping of the material, and it's is low for the nitrogen conditioned specimen, and also the recovery is more for it. So the enhanced performance, or the performance of a nitrogen conditioned or the polymer modified binder which was prepared under nitrogen conditioning was far better than the one which was prepared under the air atmosphere. So the explanation is that during the nitrogen condition, there is not oxygen, there is no oxidative aging that is happening, and also all the lighter components which were available intact for the polymer to act according or the react and perform in the polymer modified binder. So to conclude with, this non-oxidative effect should not be triggered. Suppose you're talking about the unmodified binders. When you want to simulate the long-term aging processes, the non-oxidative effect should not be triggered since they are not expected in the field. And for realistic long-term aging procedures, temperatures have to stay well below 110 degrees Celsius. And oxidative effect can be increased by other methods, by increasing the aging time or by the use of more reactive gases that are present in the atmosphere. And simulation of the long-term aging needs a thorough understanding of the influence of the aging atmosphere, the temperature, and the duration on the oxidative and the non-oxidative aging effects. Now, as far as the aging of the polymer modified binders are concerned, you have an aging, as I mentioned, that is happening during the production of the PMB itself. Then the short-term aging that happens when it is being mixed with the aggregates and compacted, and then the long-term aging. So it is very essential that one has to look into very in detail what is actually happening when you prepare a polymer modified binder before being used for the purpose for its respective purpose. So with this, let me conclude this lecture. Thank you. My acknowledgement to SERB DST for the sponsoring the project. Project number is CMR 2017-004702. Further, the results from this study will be published very soon. So thank you.